Hello guys, this is Mike coming back at you here with another video on discrete mathematics. In the previous video, we did some sample problems where we used truth tables to determine whether or not an argument or an argument form was valid or not. We saw how we fill in our truth table, we look at the critical rows, and then we look at the value of the truth value of our conclusion in those critical rows. In this video, we are going to finish off chapter 1. We're going to continue to talk about arguments and argument forms, and we're going to talk about some fallacies, some invalid arguments that people tend to commonly use, or people commonly think when they are talking in just their everyday talk, or when they are arguing some point or some topic. So from 2 videos back, we talked about modus ponens and modus tollens, 2 valid argument forms that come up quite a bit. In general, an argument form that is valid is known as a rule of inference. So in addition to modus ponens and modus tollens, we have some other rules of inference. They are listed below here. First off, the generalization. If you know that if you have 2 statements, P and Q, you know that if one of those 2 is true, then you know that the disjunction of the 2 is true. So if P is true, then P or Q is true. Similarly, if Q is true, then P or Q is also going to be true. Next up is the specialization. If the conjunction of 2 statements, P and Q, are true, then you know that each of P and Q have to be true on their own. So if I know that P and Q is true, then I know that P is true. Similarly, if I know that P and Q is true, then I know that Q has to be true. Next up is the elimination. Similar to the first one, kind of. If you know that the disjunction of 2 things is true, and you know that one of those things is false, then you know that the other one has to be true. So if I know that P or Q is true, and I know that not Q is true, which means that Q is false, then that means that P has to be the thing that's true. And similarly, if P or Q is true, and I know that not P is true, i.e. P is false, then I know that Q has to be the thing in there that's true. Fourth, the conjunction, pretty straightforward. If you know that 2 things on their own are true, then you can take their conjunction, and that conjunction is true. So if I know that P is Q, and I know that Q is true, then I know that P and Q is going to be true. Next up is our transitivity property, which says that if P implies Q is true, and Q implies R is true, then P implies R is true. This is very basic. If you think about this in terms of numbers, if I said if A is less than B and B is less than C, then A is less than C. Very, very basic. Should be pretty clear by this stage of the game. The last one is a little bit odd. Not something that we typically use very often, but this is called a division into cases. If I know that P or Q is true, and if I know that P implies R is true, and I know that Q implies R is true, then I know that R has to be true. This does come up sometimes, not so much in this course, but in higher level math classes. Certain facts or certain things you'll have to show are true, and the way you do that is by breaking what you want to show down into cases. And you work with each case and you show that it's true in each case, then you know that the thing you wanted to show does indeed have to be true. But these are just some general rules of inference to keep in mind as we continue on in this course. There's another rule of inference that we'll introduce here. We'll see it later on in this course, but you're also going to see this much more when you go on to take techniques of proof and you go on to take courses like abstract algebra and intro to real analysis, for those of you who are going to do that. And this rule of inference is the heart of a method of proof that's known as proof by contradiction. This rule is called the Contradiction Rule, aptly named if you ask me. And what it says is that if you assume a statement P is false, aka assume not P is true, and show that this leads to a contradiction. Again, contradictions we usually denote by the letter C. So that's what we have there. Then P has to be true. So if assuming the opposite of something leads you to a contradiction, then what you assumed, aka the not of something, is wrong, and the something then has to be true. And we're going to see how we use this rule and how we use this method of proof, this proof by contradiction. We're going to see how we use that later on in this course when we get to chapter 3. This can also just be stated as follows. If an assumption leads to a contradiction, then what you've assumed has to be false. That's essentially the contradiction rule in a nice bite-sized morsel. So lastly, I want to finish up with some fallacies. Errors, or times when we err in our reasoning and what we claim to be true is not actually true. The argument we're providing is an invalid argument. These errors, as I said, are called fallacies. There are a few common fallacies that occur in logic. These are sort of basic ones. These are more like things that these are more like the pitfalls that we would fall into in our everyday talk. First one is using ambiguous premises and treating them as if they are clear. Strictly from a logical standpoint, we're dealing with things that are either true or false. So in our world, in this course, in Math 270 land, this is not so much an error, but just when you're making arguments about things that are happening in life, you may be assuming some things that aren't always clear. You may not have all the information, and you may not be able to make a sound argument based on what you are assuming. 2, begging the question. You're assuming the conclusion without deriving it from the premises. This happens more often in the world of math. In some of your higher level math classes, if you take them, you'll be asked to show that if something is true, then something else has to be true. And people try to prove that using the conclusion of that problem that they were given. Third one is jumping to a conclusion without adequate grounds. Namely, this is trying to arrive at the conclusion of your sentence or of your problem without showing that the hypotheses are necessarily true. You have the bridge that leads you to the other side of the canyon, if you will, and that bridge isn't necessarily built all the way. You don't necessarily have that clear path to the other side of the cliff. So these are just some basic fallacies. We see these more often in our everyday talk. but these do show up in mathematics as well. There's two more fallacies that I want to look at as we finish up this video. These are also argument forms that are invalid. The inverse error and the converse error as well. First up, the converse error. This is also known as affirming the consequent. If you know that P implies Q, and you know that Q is true, you can't necessarily conclude anything about P. The error is that if you know that P implies Q, and you know that Q is true, people will then mistakenly think that P has to be true. That is not the case. If you go back to the truth table for the conditional logic operator, you know that in the column where we have our implication, P implies Q is true when P is true and Q is true, or when P is false and Q is true. So just because we have a conditional that we know is true and we know that Q is true, that doesn't mean we can conclude anything about the truth value of P. Number two is called the inverse error, also known as denying the antecedent or the hypothesis or hypotheses. Again, we assume we have a conditional or an implication that we know is true, and we also know that not P is true. We can't then necessarily conclude that not Q is true. Again, if you think back to the truth table for the conditional logic operator, when not P is true, aka true, P is false. I'm combining my trues and my falses here. If P is false and our implication is true, we don't know for sure that Q is true. Q could be false as well. P could be Q could be true or Q could be false. So we can't say anything about not Q. So this is the final video for chapter 1. I apologize for the word jumbling, but these are just some basic fallacies that we encounter in math as well as in everyday talk, and just things to be on the lookout for next time you're working on math problems or you're carrying on a debate or an argument with somebody. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.